Okay, so when we left off, we were just talking about the fact that the formula for period is delta t over n. And so when you divide time by just a number, you're going to get a unit of seconds, which makes sense because the definition of period is the amount of time it takes for one complete cycle. For frequency, the equation is just the opposite. It's how many cycles happen in a certain period of time. And that's going to give you a unit of 1 over seconds. And you won't ever hear that. Instead, you'll hear it as hertz. And if you think of your computer, how many megahertz, how many gigahertz, right? And so a hertz is simply equal to a 1 over a second. And so and the abbreviation is HZ. Okay? But look at our two equations, one for period and one for frequency. Delta t over n, n over delta t. Hopefully you notice they're just the opposite, the flip, or the reciprocal of each other. Which means that t is equal to 1 over f, and f is equal to 1 over t. So if you have one of them, you can find the other. Like if you, so this was 3 seconds, so instead of, for frequency, instead of dividing 10 by 30, you could have just said, oh, if period is 3 seconds, then frequency is going to be 1 over 3 hertz. Okay, so it's just going to be the reciprocal. All right, so that's period and frequency. Now, the one thing about frequency, though, is what is frequency? So in a ripple tank, frequency is how many times I tap my finger up and down, how many times per second, to figure out how many cycles are going to go out in a bathtub or whatever. In sound, frequency has a special quantity. You will hear it in sound in a different way. Can you figure out the way? I could give you a hint. It's going to do something different. It's going to have a different frequency than when I talk like this. Frequency in sound is the pitch. And those of you in music probably got that because you would know different frequency really means different pitch. In light, frequency also this time can be seen. So in sound, right here in your notes, it'll be, in sound, frequency is the pitch. In light, any ideas what frequency might be? Take a look at each other and say something. I'll wait. If you said color, you would be correct. So all the different colors in the rainbow are there because there's different frequencies of light. Okay? Now what is it that determines the frequency of a wave? Well, I gave you a hint when I talked about the ripple tank. If I want to change the frequency of a wave, I change the frequency of the source that's creating the wave. So I can tap my finger up and down really quick or really slow. And if you can imagine the bathtub, you would see a whole bunch of waves going out together if it was really fast, or a gap between them if my finger was going up and down slower. Okay, so once though the wave is created, the frequency is set because it's set by the source. No matter what medium the wave goes through, no matter what happens to it, the frequency will not change. So if I had a highlighter and I were you, I would highlight this part. The frequency of a wave is determined by the source of the vibration and therefore does not change as the wave travels from one medium to another. Didn't say it earlier, but up here I would have highlighted the part about the amplitude. The amplitude of the wave tells us about the energy the wave is carrying. And then the bottom line, the wave does, one cannot change the speed as one adds energy, one only changes the amplitude. Okay, but back to frequency. The frequency can't change once the wave is created. The only way you can change the frequency is by changing the source of the vibration. All right, next up is a very famous equation. It's known as the universal wave equation. Universal wave equation. And it actually comes from your grade 10 equation. It comes from VAV is equal to delta D over delta T. Okay? So if we want to find the speed of a wave, well, the delta D, we often, when we talk about distance, we often think of a wavelength. So if we switch the delta d to lambda, then on the bottom we would have 1 over the time. And 1 over the time is really like the frequency, 1 over the period. And so our universal wave equation is v equals f lambda. Okay, so in this unit you will sometimes use v equals f lambda, but if it tells you the distance it travels in a certain period of time, you'd still use your grade 10 equation. So we have really, these are the 4 main equations for this first part of the unit. Period and frequency, how they're related, the reciprocals, the grade 10 equation, and our new one, the universal wave equation, v equals f lambda. Now let's talk about the speed of a wave. The speed of the wave is actually determined by the medium through which it moves. Well, moves, you know. We talked on Friday about the fact that if some waves travel through air, they go faster, like electromagnetic, whereas in liquids they go slower. But in another type of wave, mechanical, they travel fastest in solids and really slowly in air. Electromagnetic travel the fastest that they can travel in a vacuum, whereas mechanical, they can't travel in a vacuum at all. So the speed of the wave is determined by the medium. That's what determines how fast the wave will move. And if a wave changes from one medium to another, its speed will change. So if light's traveling through an air and then enters a tank of water, it's going to slow down. If a wave is traveling through the water and then comes out, if it's a sound wave, through water and then out into the air, its speed's going to change. So the medium is what determines the speed of the wave. Sometimes we think that, like, if you're in the ripple tank again and you're tapping your finger or in the bathtub, or if you had a really, really huge, like maybe jacuzzi, but the jets aren't turned on, and you tapped your finger, you might see the wave like start out big, but as it goes on and on, it dies out like this. Right? Until you can't see it anymore. The unphysicsed among us would think that this means the wave's slowing down, but it isn't. A wave in a particular medium travels at a constant speed, and the only way you change the speed of the wave is change the medium that it's traveling in. What's going on here is that the wave is losing energy to its surroundings, right? Because remember, amplitude is energy. So it's losing energy to its surroundings, but it's still traveling at exactly the same speed. It travels so some people would think this means the wave stopped. Nope, it's just died out. But even when it has the last little smidgen of energy that only has enough energy to move a molecule a tiny little bit, it's still traveling at exactly the same speed as it was up here when it had a huge amplitude. So its speed is constant in a medium. The amplitude is the energy that it's carrying, but it has nothing to do with how quickly that energy is being passed through the medium. So when you can't hear someone, it's because the amplitude dies out, and so the wave no longer exists out here. It's not that it stops, it's just no longer in motion. Okay? One last thing. On your sheet, I could just show you. On your sheet here, I have a wave pattern, and it says, in the next instant in time, what way would point B move if the velocity is going to the right? So take a minute, because the video is about to run out. Before you start the next video, at your tables, come up with which way do you think B is going to move. Up, down, sides, which way it's like. So right now I've frozen this in time, and when I unfreeze it and the wave continues to travel to the right, what way will particle B in this wave move? Okay, so everybody needs to have a choice, so you can talk with each other at your table for a minute, and then start the next video and we'll find out.